Every AI agent is really just three things working together: a language model, the context it's given, and the tools it can use. Today we're going deep on that middle piece, context, because it turns out to be the part that determines whether an agent actually works. Context is the ceiling of agent capability. Language models perform incredibly well on standardized tests, but they often stumble in real business settings. Here's why. Model capability is general purpose, but every real task depends on local knowledge. Product architecture, business rules, internal conventions, none of which lives inside the model's parameters. Think of it like hiring a brilliant new engineer. They may have deep technical skill, but they don't yet know your product, your codebase, or your team's unwritten rules. Give them nothing to go on, and even genius struggles to deliver. The same is true for an agent. The takeaway: model capability is the floor, but context is the ceiling. A moderately capable model with excellent context will often outperform a stronger model working with poor context. Anatomy of context. A coding agent example. Let's make this concrete. Say you tell an agent, "Help me fix this bug." Whether it can actually do that well depends on three categories of context. First, code context. The structure of the codebase, what each module is responsible for, and the coding standards in place. Without it, the agent might write code that runs but doesn't fit the project's architecture. Second, process context. Branching strategy, commit conventions, review requirements. Skip this, and the agent might commit straight to the main branch without testing. Third, environment context. Local setup, test database credentials, deployment steps. Miss this, and a fix that works on a laptop breaks the moment it hits staging. All three are the baseline requirement for an agent to be useful. Context engineering is organizational, not just technical. Here's a shift in perspective. A lot of critical knowledge inside teams is tacit. It lives in senior people's heads or scattered across private conversations. That's a terrible environment for an AI agent to operate in because it simply can't see any of it. Now compare that to how long-running open-source projects work. Public discussions, recorded decisions, a documented history anyone can read. That same transparency that makes a project welcoming to new human contributors also makes it naturally friendly to AI agents. So here's the practical framing. Treat every agent task like onboarding a brand new team member. Give it enough background, and it can do great work. Give it nothing, and most of its intelligence goes to waste. Building an AI-ready team, in the end, is mostly a documentation exercise, not a tooling purchase. Context at the API level. 4 message roles. Let's get technical for a moment. Under the hood, every call to a language model is built from a list of messages, and each message has a role. System messages are developer-written instructions, the agent's identity, its rules, its constraints, usually set once at the start. User messages are the actual input from the person using the agent. Assistant messages are the model's own previous outputs, including any tool calls it made. And tool messages carry the results of those tool calls back to the model, each one linked to its specific request through an ID. Tool definitions themselves live in a separate field entirely. They're not messages. Understanding this structure matters because almost every technique we'll cover comes down to how you populate and order this list. The simplest case, a single turn call. In the simplest possible interaction, a request is just a system message plus a user message, and the response is a single reply. But here's the crucial detail. Every one of these calls is stateless. The model has no memory between requests. If information matters, it has to be included in the request. Every single time. That statelessness is the foundation for basically everything else we're going to talk about. Multi-turn tool calling, the agent's core loop. Now let's add tools into the mix. Say someone asks, "What's the time and weather in Vancouver?" The model can't answer that directly. It doesn't have real-time data. So instead of replying with text, it returns a request to call two tools. The framework executes both, in parallel since they're independent, then sends the entire conversation back to the model, including those fresh tool results. Only then does the model generate its final answer, or decide it needs to call more tools. This request, execute, return, repeat cycle is the heartbeat of how agents actually operate. The agent looping code, strip away the abstraction, and an agent is fundamentally a loop. Call the model, check if it asked for a tool. If it did, run that tool and append the result to the conversation. Then loop back and call the model again. If it didn't ask for a tool, that's the final answer, and you're done. Nearly every technique for improving agent performance comes down to improving what goes into that growing list of messages, not changing this loop itself. Context composition, static prefix plus growing trajectory. Every model call has the same basic shape. There's a static prefix, the system prompt and tool definitions, which stays the same for the whole conversation. And there's a trajectory, the user messages, model replies, and tool results, which keeps growing with every turn. Keep that mental picture in mind because it's the key to understanding caching, dynamic loading, and compression, which are all really about managing these two halves differently. The timestamp incident. Here's a cautionary story. A production customer service agent was handling 100,000 conversations a day, running smoothly. Then an engineer, wanting the agent to always know the current time, added a live timestamp directly into the system prompt. The very next day, alerts started firing. Response times jumped from half a second to 3 to 5 seconds, and the monthly inference bill nearly doubled. Nothing else had changed. The code looked fine, the model was the same. The problem was that single changing line. Because the timestamp was different on every request, it broke the system's ability to reuse previously computed results, forcing a full, expensive recomputation every single time. 3 rules for cache-friendly context. If there's one thing to remember from all of this, it's these 3 rules. First, once your system prompt and tool definitions are finalized, don't touch them. Second, anything dynamic, timestamps, live counters, changing state, should be appended at the end of the conversation, never edited into the front. Third, use the standard structured message format. Don't hand-roll your own text formatting. Break any of these, and you can silently multiply your latency and your cost by an order of magnitude. Why it works. Attention, Q/K/V, and the cache. Here's the intuition behind why this matters so much. Inside the model, every word generates a query, essentially a question about what it's looking for. It compares that query against a key from every earlier word. Think of it as a label. Where there's a strong match, it pulls in that word's value, its actual content. Now, without any caching, every new word has to redo this matching process against every previous word from scratch. That means the total computation grows quadratically as the conversation gets longer. Caching solves this by storing those keys and values once they're computed, so new words only need to compute their own, not recompute everyone else's. From messages to tokens, the chat template. The structured messages we've been describing aren't actually what the model reads directly. They get translated into a single continuous stream of tokens using special markers that indicate where each message starts, ends, and whose turn it is. Different model families use different formats for this translation. This matters for 2 reasons. First, if you bypass the standard format and manually glue together your own text, you weaken the model's ability to reason across multiple steps, because it was trained on the proper structured format. Second, this translation process is exactly why even a tiny change, one extra space near the beginning of the prompt, can break the entire cache. 2 levels of caching. There are actually 2 distinct types of caching happening, and it's worth telling them apart. One works inside a single model call, It avoids recomputing information as the model generates each new token. The other works across separate requests. If two calls share an identical prefix, the second one can reuse cached work from the first instead of processing it again. Reading from that cache typically costs around a tenth of doing fresh computation. Both types depend on keeping your prefix stable, but the cross-request one is the one that shows up directly on your bill. Caching as an architectural constraint. In serious production systems, caching stops being just a performance tweak. It becomes something that shapes the whole architecture. The order you put information in your prompt starts being driven by what maximizes cache reuse, not just what makes logical sense. Every extra condition you place near the front of your prompt, say 3 different binary settings, multiplies out into 8 different possible prefixes, each needing its own cache entry. When one agent spawns a sub-agent, that sub-agent's prompt needs to align byte for byte with the parent, purely so it can hit the same cache. Even placeholder text used to summarize large tool outputs gets frozen the first time it's generated and reused exactly, forever, just to preserve cache consistency. The lesson: the earlier you design around this constraint, the less it costs you later. Anti-patterns that quietly wreck performance. Let's go through 5 patterns that look completely reasonable but cause real damage. Putting a dynamic system prompt with live values like timestamps. Injecting dynamic user configuration data directly into context on every request. Reordering your tool definitions based on how often they're used. Using a sliding window that only keeps the most recent messages. This one is especially sneaky because it doesn't just break caching, it can also throw away a critical piece of information the agent will desperately need later, causing it to loop and repeat the same actions. And finally, manually flattening structured messages into plain user says, assistant says text, which confuses the model about who's actually speaking. Prompt engineering, tone, structure, process. Good instructions have a few common traits. On tone, hard constraints, like keep responses under 4 lines, shape behavior far more reliably than soft suggestions. On structure, using clear tags around information helps the model immediately understand what kind of information it's looking at. And lightweight formatting like headers and bullet points adds readable hierarchy on top. And on organization, instructions written as a clear step-by-step process consistently outperform a long, unordered pile of rules. In one controlled test, simply removing the hierarchy and structure from an otherwise identical set of rules caused task success to drop by more than 30%. A good gut check. If a new hire read these exact instructions, would they know what to do? If not, neither will the model. Turning business rules into executable instructions. Here's a scenario. An agent negotiates bills on someone's behalf, and there are different pricing models depending on the situation. A commission if it saves money, a flat fee for simple bookings, an upfront payment for very difficult tasks. The problem is that vague guidance like choose the appropriate pricing based on the situation leads to wildly inconsistent behavior. Is cancelling a subscription saving money? Reasonable people could disagree, and so will the model, inconsistently. The fix is precision. Rules need to be specific enough to actually execute, like explicitly stating that commission-based pricing should never apply to refunds or cancellations. This kind of precise rule writing is best done by the people who deeply understand the business, with engineers responsible for encoding it accurately, not guessing at business logic themselves. Few shot examples. When showing beats telling, sometimes the desired output is hard to describe in words, a particular tone, a specific formatting style. In those cases, 2 or 3 well-chosen examples often work better than pages of abstract description. But quality matters more than quantity. 2 or 3 examples that cover different edge cases beat 10 examples that are all nearly identical, which just eat up space without adding much value. And one practical note: once you've picked your examples, keep them fixed. Dynamically swapping in the most relevant example for every single request quietly breaks the caching benefits you'd otherwise get. Tool definitions and progressive disclosure. Just like the instructions you give a model, the descriptions of the tools it can use matter enormously. Good tool descriptions spell out usage boundaries, give concrete examples, and clarify how tools relate to each other. And there's a newer technique worth knowing. Instead of loading the full technical details of every available tool up front, systems can show the model just short summaries first, and only load the complete details for a specific tool once the model decides it actually needs it. Because of how the underlying computation works, appending that detail later doesn't disturb anything that was already cached earlier in the conversation. It's purely additive. Prompt injection, the core security threat. Here's a serious risk. Anything an agent reads from the outside world, a web page, a document, even hidden metadata in an image, could contain disguised instructions planted by an attacker. And this is far more dangerous for an agent than for a simple chatbot, because an agent can actually take real-world actions, sending emails, deleting files, moving money. The core defense is helping the model clearly distinguish between trustworthy instructions and untrusted data it's merely processing. That means clearly labeling external content as untrusted when it enters the conversation, strictly keeping structured roles intact rather than blending everything into generic text, and filtering for obviously suspicious phrases as a weak but useful extra layer. It's worth being honest, though. None of this is a complete guarantee. Real protection also requires limiting what actions the agent is allowed to take without a human checking first. Loading knowledge on demand. As an agent takes on more and more types of tasks, cramming every piece of specialized knowledge into one giant set of instructions stops working. It wastes space and dilutes the model's attention to what actually matters right now. A better approach loads specialized knowledge in layers. First, lightweight summaries for every available knowledge module are always visible, so the model knows what's out there. Second, when a task actually matches one of those modules, its full core instructions get loaded. And third, if even more depth is needed, additional detailed reference material can be pulled in selectively. It's the difference between memorizing an entire library and simply knowing which book to grab off the shelf. Where should that knowledge live? This turns out to be a genuinely tricky engineering trade-off. Option 1. Put the knowledge directly in the core instructions. The model follows it extremely well, but every time you swap in new knowledge, you break your caching and pay a steep performance penalty. Option 2. Have the model read it in mid-conversation, like a regular file. This leaves your cache completely intact. But weaker models sometimes don't treat that content with the same authority as a direct instruction. They might just skim it like ordinary output. The practical solution production systems use is a hybrid. Keep lightweight summaries always visible for routing decisions, and load the full content only once it's needed, after which it simply rides along as part of the cached conversation for the rest of the session. A real-time dashboard for the model. Picture the status bar at the top of your phone: time, battery, signal strength. It's not the main content of anything you're doing, but it's always there, giving you a quick read on the state of things. Agents benefit from the exact same idea: a running summary. How many actions have been taken, how much of the task is done, whether any limits have been hit, refreshed and placed at the end of the conversation. Here's the underlying reason this helps so much. Models are excellent at finding a specific piece of information buried in a long context, but surprisingly unreliable at tallying or summarizing that information on their own. Ask a model how many times it's already called a particular number, and it'll often get the count wrong. Not because the information isn't there, but because counting it accurately requires extra reasoning it doesn't always do well. A dashboard solves this by doing that counting once, explicitly, instead of asking the model to rederive it every single turn. Measured impact. This isn't just a nice theory. It's been tested at scale across 11 different models and tens of thousands of evaluations. For weaker models, adding this kind of running summary boosted accuracy by 40 to over 50 percentage points, enough that a small, lightweight model could match a much more powerful one that didn't have this advantage. For stronger models that were already getting the right answer, the benefit showed up differently. They needed dramatically less internal reasoning to get there, cutting the computational cost by somewhere around 80 to 90%. And here's the most striking part. Without a running summary, the amount of reasoning needed keeps climbing the longer a conversation goes on. With one in place, that cost stays roughly flat no matter how long the conversation runs. So here's the through line. First, carefully design what goes into the model's stable instructions. Protect that content from being hijacked by outside data and load specialized knowledge only when it's actually needed. Second, keep the model continuously aware of its own progress and state through a running summary at the end of the conversation. And third, which we'll dig into separately, manage the ever-growing history of a long conversation so it doesn't spiral out of control. Put those three pieces together, and you have a genuinely well-engineered context. One that lets a model's raw intelligence actually translate into reliable, real-world performance.